Hello there, welcome to Susan and John Math Tube. Today we are going to discuss about probability distribution functions. And I expect all the students who watch this video to be very good in the basic concepts of probability. In probability distribution function, what we try to do is we try to convert probability into a function form. We think as if probability is a function. And I'm sure in your high school you learned a lot about functions. So function can transform elements into another elements or other elements. So basically function is a rule. Likewise, we are going to change probability into a function. Of course, the output will be probability values. So take a look at the above function, which is the squaring function. If I input the value 4, I'll get the output 16. If I input the value 10, I'll get the output 10 square, that is 100. Likewise, I'll input certain values which will be related to a random experiment. But the output will be the probability value. And basically, that is what a probability function does. So let's move ahead and you can note this definition. So PDF or the probability distribution function is a technique which will convert real life events into a probability model. So what we do is we'll do some sort of experiments and we will have the output as probability. That is, we try to visualize the experiment from a probability point of view. Or rather, we use the probability values and we learn about the real life events. Okay, to understand further, you need a few definitions. So, I hope you remember the basic model of a function. Let's say f is a function which connects two sets a and b, and a will be called the domain and b will be called the codomain, and the function values which will be inside b is called the range. So remember, the input values are called domain values, and in probability distribution function the input values will be related to a random experiment, and the variable which we use to denote the input is called a random variable. As always, I'm going to ask you one question, and I'm sure you know that question. Do you have a paper and a pen? If not, pause the video right now and get a sheet of paper and pen. I want you to note all these points. Okay, let's move ahead. So, the output, like I told you before, a function will have input, that is called the domain values, and the function will have a set inside which we write the output values, and that is called the codomain. And in a probability distribution function, the input values will be related to a random experiment. The input variable is called the random variable, and the output values will be nothing but the probability values. Okay, basically a probability function will look like this. So we have a domain and the input will be related to some random experiment, and we will find the probability value of each and every input, because in a function every value in the or every element in the domain should have an output, and the pink colored ones will define the range. And remember one thing, the random variables, I hope you understand what is meant by random variable. The variable which we assign for the input will be denoted by capital letters. Normally we go for capital X, capital Y, capital Z, etc. And the possible input values of X will be denoted by small x. You'll understand all these things when we go for an example. If it is Y, then we use Y. So basically it will look like this. Capital X is the input and small x means all possible input values. Anyway, let's go for an example. Okay, so are you ready with your pen and paper? So tell me, what will happen if you toss three coins simultaneously? What are the possibilities? Think about it. If you toss three coins simultaneously, what are the different possibilities? Don't tell me the coin is going to stand and you'll get both head and tail. Let's ignore that. Let's hope when you toss the coin you'll either get head or tail. So one possibility is like head, tail, head. And another possibility, can you try? Maybe tail, tail, and all of them tail. So there are many possibilities. So let's go for the sample space. So let H represent the head and T represent the tail. So the sample space will be 1, 2, 3, 4, 5, 6, 7 and 8. There are 8 possibilities. Of course, because 2 into 2 into 2, that will be 8. Now, I'm trying to create a probability function out of this experiment. So I hope you're okay with the experiment. We tossed 3 coins simultaneously and this is the sample space. Let x be the random variable associated with the number of heads. So look at this. You can see that sometimes we are getting 3 heads and in some other cases we are getting 2 heads and in some other cases we are getting only 1 head at a time and sometimes no head at all. So look at this. We have a random variable that is associated with the number of heads. So the possible values of x, can you guess the possible values of x? Yeah, x can be 0 because take a look at this case. Maybe x is equal to 1. You can check out 1, 2, 3. See, 1 head. Maybe x can be 2 or 3. So this is our capital X, as I told you before, the random variable, and these are the possible values of capital X. Now what we do is we are going to create a function. What sort of function? Probability function. And we have the input values 0, 1, 2 and 3. Okay, I'm not going to write the codomain, but I'll write the range values. So tell me, what is the probability I'll get capital X is equal to 0? Capital X stands for the number of heads. You can read over here. So tell me, what is the probability I will not get any head? Yeah, only one case. That means the probability will be 1 upon 8. Now tell me, what is the probability x is equal to 1? What do you mean by x? X is associated with the number of heads. As you can see in the sample space, 3 members support the event x is equal to 1. So the probability will be 3 by 8. And similarly, what will be the probability of x is equal to 2? X equal to 2 means there should be 2 heads, and you can check the sample space and the answer is again 3 by 8. and finally the last one 1 by 8. So look at this. This is called a probability distribution function. So look at this. We have a random experiment, and from the random experiment we have a sample space. And then what we did is we defined the random variable that is related to the experiment. Now we found all the possible values of x. Then we modeled it using probability. And this is called a probability distribution function. But normally in the statistics books, you will not see this picture. You'll see something like this. And this table is called the probability distribution table, or simply the discrete probability distribution. Discrete in the sense we are using the numbers 0, 1, 2, 3. We are not moving in a continuous scale, but we are using the numbers 0, 1, 2, 3. We don't consider then all the numbers between 1 and 2 or maybe 0 and 3. Okay. So we have our random variable and we have the output as probabilities. Okay. So shall we move on to one more example? Okay. So I want you to read the question very carefully. So we have a statistics student and he travels to his college by bus. And normal, this is quite normal to the statistics students. They want to predict. They literally want to predict everything. So he wants to predict the bus arrival time in his bus stop. So the next thing is very important. There is something very important for the statistics students. Observation, collecting data. So what did he do? He started collecting data. He observed for 100 working days. So what did he do? He observed the bus time for the next 100 working days. Okay, and here's some assumptions. That is, the bus and the driver are always same. He used the conditions so that there will be not much for the homogeneity purpose. Because if you have a different bus, maybe a more powerful one or maybe an old one, the time might change. And if you have another driver, the same thing. So he has some assumptions over here for his experiment. The bus and the driver, and I guess the driving conditions, the route, etc., are supposed to be same. Okay, and these are his observations. Now look at this. The time in this experiment is rounded to the nearest minute. So intentionally he made the experiment into a discrete one. So we can see that the bus never comes before 6:29. As he's going to college, let's assume this is morning. Yeah, we don't need that data anyway. Okay, so the bus never comes before 6:29 or after 6:34. And how many days did the bus come at 6:29? Wow, that's very less. Only 1 out of 100. And 6:30 3 times, 31, 41 times, etc., etc., etc. Look at this. Now we have a random experiment. And look at this. We create the random variable. Do you remember I told you before? Random variables will be denoted by capital alphabets. So T is the discrete random variable associated with arrival time. So what are the possible values of capital T? You can see 629, 30, 31, 32, 33, 34. So I'm supposed to write all those things here. 629, then 630, 631, 632, 633, and finally 634. And this is our domain. So tell me, what is the probability the bus will come at 629? According to the data, can you guess? Yeah, 1 out of 100. He observed for 100 days, and only for one day it came at 629. So what's the probability? 0.01. And what is the probability the bus comes at 6:30? You can see that it's like 3 out of 100. So I'm going to write 0.03. What about 6:31? Wow, that's a lot. That's a lot. So we have 41 out of 100, that is 0.41. And at 6:32 it becomes 0.35, and then 0.14, and finally 0.06. So we have all the probability values over here. So this will be the probability distribution function for his experiment. So did you understand? We are converting the real life events into a probability structure. And using this probability structure, we will be able to predict many things about the original event. So, as I told you before, in your statistics books, you'll never see this picture. You're never going to see this picture, but instead, you'll have a table. A table with input values, time, and output values, as always, probability, because the function is probability function. So this is exactly what you will see in your statistics books. So we have the possible input time over here, and we have the corresponding probabilities. And now my question is, what are the things you observe from this table? I gave you two examples. I'll give you a minute, so please think about it. You can pause the video and think about it. The first thing I can observe is none of the probability values can be negative. And I can observe one more very important thing, that is, if I add all the probability values, can you guess? The answer will be equal to 1. So here it goes. So if you add all the probability values, let it be any probability distribution function, if you add all the probability values, the sum will be equal to 1. And the next observation, I'm sure when you learn probability in your high school, you learned that probability is a non-negative value. The value always lies between 0 and 1 inclusive. So these values can never ever be negative. Now the next thing is expectation. So what do you expect from this table? Because there's a big question. When will the student's bus arrive in his stop? So what might be your answer? I'm sure most of you will tell me the answer 631. But there's a little bit possibility it can be at 632 also, because these two numbers are like probability is really high. So that is why we need expectation. In statistics, you have learned that expectation means arithmetic mean, because when you're given a data, when you're given a data and when you find the arithmetic mean, you get the expected value from the data. Okay, so what's the formula for arithmetic mean? I hope you remember this sigma xi fi by n. And I hope you don't mind if I take this n inside the summation. And then what I do is I'm going to write this as xi into fi by n. Take a good look at this quantity fi by n. And I'll remind you what we did in the last example. At 6:29, the observation was 1. And how many days did the boy perform the experiment? For 100 days. So what did you write as the probability value? 1 by 100. And now you may understand that this fi by n is nothing but our probability for the ith data. So I'm going to change the formula for our arithmetic mean into sigma xi pi. Applying the same logic, we get variance to be this one and standard deviation to be root under variance. So look at this. In the last example, the boy was trying to calculate the bus arrival time. So if he finds the expectation is nothing but the arithmetic mean, he'll get something very near to 631 or 32. Okay, and there will be plus or minus. The bus does not arrive to the stop consistently every day, so he will calculate the standard deviation. Now he'll have a clear idea, that is, he might do expectation minus standard deviation and expectation plus standard deviation, and that will give him a very clear idea about the bus arrival time. My friends, I'll repeat once more. So we have a random experiment, and the random experiment will be converted into some numerical values or numbers by using our random variable. And then we calculate the probability values for each and every possible value of the random variable, and that gives us the probability distribution function. The points to remember: the first one is capital X is called discrete random variable. Then we have the probability distribution function or the probability mass function, which looks something like this. So we have the input values or the possible values associated with the experiment and the corresponding probabilities. And the first condition, all the probability values must be positive. And the second condition, if you add all these probability values, you're going to get 1. And the third one, the expectation or the arithmetic mean. The expectation is nothing but sigma pi xi. And then comes variance and of course the standard deviation. I'm going to end this video with this, and If you want us to make videos related to any particular topic in math or even in probability, then feel free to email us at sjmathtube@gmail.com. And in the next video, we'll be discussing about problems based on discrete probability distribution functions. So till then, bye.